Okay, continuing on with Biology Paper 1, 2018 AQA. Question 2 here. Question 2 is a question on osmosis. Okay, so this is saying a student investigated the effect of surface area on osmosis in cubes of potato. He cut 2 cubes of potato tissue, each with sides of 35mm length. And he put 1 cube into concentrated sucrose solution. Not sugar, nor sucrose, but sugar. He cut the other cube into 8 equal sized smaller cubes and put them into the sucrose solution, the same concentration as used for the larger cube. And then he records the masses of the cubes. Now you can see here that B suffers a decrease in mass at a faster rate than A. Let's say up here what A and B are, interestingly. That doesn't matter. Okay, let's get rid of that. Okay. So 2.1, what they want to know is they want to know the method. The method might have been used. Describe the method the student would have used to obtain results in figure 3. Starter, after all the cubes of potatoes have been cut, also consider the variables he should have controlled. Okay. Couple things to think about here. The variables controlled. As you know from GCSE, you know what's kept constant. The thing that's varying, the independent variable, as sometimes called, is the surface area. So other things we want to keep the same, and this is where most of the marks are coming from here. The classic one is to control temperature. Often you think about water bath or something like that. It's not really appropriate here. Just say keep it at room temperature. Oops. Damn cat. For A and B. Boom, 1 mark point. Now when you take the large cube, damn cats, large cube and smaller cubes out, you don't want surface water, these be 8 of these. I'm only going to draw 2. Times 4. Cat. You don't want surface water affecting weight or mass. So they say here, let's just check what the diagram shows. Total mass in grams. So, I mean, if you do this experiment in class, what you do is blot, dry. With towel, paper towel. So that all you're measuring is the mass of the potato cube after it has undergone some osmosis. So that is a good point to put down. That's another good point up there. And if you look at this graph here, we see that we've got time intervals. So the thing is to use figure 3 for your method. You want time intervals to weigh whatever's reasonable, something like every 10 minutes or so. Should do it. That's a third mark point. Another one that's in the mark scheme here. I mean, yes, I've seen the mark scheme. I know what should be said. But if you've done this kind of experiment, you're thinking about control variables, how you do it, what is going to upset the result potentially. There's logical things that you apply to all sorts of different experiments. Another thing here is you want exposure of surfaces to solution. So maybe you want some kind of agitation. You know, some sort of plate that's rotating or moving in a kind of, you know what I mean? It's sort of mixing up the potatoes so they're not all settled at the bottom like that. They're kind of kept in suspension. I'm not going to write that all out in words. That's the kind of thing that they're looking for, though. Okay, next. Okay, these later papers after the 2015 reforms, questions can tend to be a bit harder, and they like their maths questions. So here we go. Here's a maths question. Come on. Okay, so this says, the loss in mass shown in the figure is due to osmosis. Cool. The rate of osmosis between 0 and 40 minutes is faster in B, the 8 small cubes, than in A. The rate of osmosis per square millimeter per minute is the rate of osmosis different between A and B during the time. Right, okay. I'll just get that page in here. It's a bit bigger. Right. We got 0 to 40 minutes. Do rates of osmosis differ? Question. Per square millimeter. Okay, so there's a change in mass, which is measured in grams. So our rate, I'll get that off. Our rate is in grams. Per square millimeter. Per minute. All right, so this is total surface area. Okay, so which is the big cube, which is the small cube? A and B. One large cube. One large cube is A. Okay. So that has fallen from 62 down to 57. Look at A here. 62 minus 57 equals, my maths does not defeat me. Right, so A's lost 5 grams. B, again, it's on 62. B falls to 53. 9 grams lost. And so that's the, let's just remind ourselves that B are the small cubes. Okay, so A has dimensions of 35 millimeters. It's that face there, 35 by 35, 35 deep, but we're not looking for cubic area, we're looking for surface area. So the area of one face is 35 times 35. And then we would times that by 6. Get total area. Let's get my calculator. 1 second. Cat. No. Okay. So 35 times 35 times 6. 7350. Square millimeters. B. So with B, let's make a different color here. That's a nice red. No. I kind of cut like this and this and on that axis as well. So with B, you've got, let's go back to this guy here. With B, you've got half 35 is 17.5 times, so it's like that one there, times 17.5. Let's make a bit of a mess here. This is where you touch the iPad. Times 6, and then you got 1, 2, 3, 4, and then the 4 behind you've got 8. So that's the surface area of one cube. but you've got 8 of them. And this should be a higher surface area than this one above. So 17.5. This is a lot of work for 3 marks. Leave this to the end of the exam. Times 17.5. Times 6 times 8 equals 14700. And I'll just check the mark scheme here because that's probably a mark point. Surface areas. Not yet. Wait a minute. Allow 1 mark calculation. Yeah, those 2 there. All that work. That's 1 mark. AQA, they're lovely, aren't they? Right, okay. So now, per minute. So we got here. Grams per square millimeter per minute. Okay. So what we've worked out so far, 9. Is a change in mass in grams and the surface areas. Right, so for A, we got 5 grams. Shouldn't do that. Damn thing. Really annoying. 5 grams. For 7350 square millimeters in 40 minutes. All right, so we want that to be calculated as gram per square millimeter, and then per min. All right, so we've got 5 grams divided by 7350 equals 0.0068. Leave that in the calculator. And then divide by 40 to get it per minute. Equals I hope you're following the math. So, it takes a lot to kind of explain it all. 1.7 times, so we got 1, 2, 3, 4, 5 times 10 to the minus 5. Grams per square millimeter per minute. Okay. That is the rate of osmosis of A. The rate is how much mass is lost in grams over 40 minutes, which is the time period they asked you to look at, and is calculated per square millimetre. Right, now all you got to do is fill this in for B, same method, but I'm not going to write all that out. And when you do B, you get, what did I work it out? Well, in the mark scheme, they've got 1.5 times 10 to minus 5 to 1.6 for the other one. Let's just call that one B 1.5. Sorry about that. That's very scruffy. That's terrible. Times 10 to the minus 5 gram per square meter per minute. And is that a significant difference? They're close. The question is is the rate of osmosis per square millimeter per minute different between A and B during this time? So you can say yes or no. They're close. So no, they have a what you consider a significant difference. So they are different, but the marks are from the calculation, which is not a simple one, and it takes a long time. Good old AQA. So I would say, in my opinion, yes, significant difference. A greater than B, which is a little surprising really, because if we look back, A being the large cube seems to have a higher rate, even though its surface area would be lower. But I think they like to confuse like that, to kind of stress your logic. All right, that'll do for now. Question 3 to come next. Adios.